we're going to continue talking about applications of derivatives. So far, we've discussed the meaning graphically and physically of the first, second, and third derivatives. We looked at number line analyses. We looked at curve sketching. So what we're talking about today is a series of problems that are called min-max problems that are going to use a lot of the ideas behind what we talked about. Because min-max, that's just finding turning points on graphs. So how, once again, do we find a turning point on a graph? Well, given a function f of x, we know that a turning point occurs where f prime of x is equal to 0. So all we have to do in these problems is create the correct function, take the derivative of it with respect to what we're trying to maximize, set it equal to 0, and solve. But let's see how this goes in practice. So we're going to be using the applications of derivatives worksheet, but before we get to that, let's do a different problem. Let's say I toss a ball upwards at, I don't know, 20 meters per second, and I want to know the maximum height. Okay, so let's rely on your knowledge from last year to set up a function. So what I want to know here is a y max. But what function can I set up here? Well, I actually know that I can set up the y displacement as a function of time here, because I remember, hopefully, the equation vit plus 1/2 at squared. If I call up positive, then this function is going to be 20 meters per second times t plus 1/2, and we know the acceleration due to gravity is 9.8 meters per second downwards, or in this case, because up is positive, negative 9.8 meters per second, t squared. So the height, delta y, or the vertical displacement as a function of time, is equal to that. Let's make this just a little bit easier. I'll actually do, if I make the initial y position equal to 0, then delta y is the same thing as y final, which is just going to make this a little bit easier. So y final as a function of time then is just 20t minus 4.9 t squared. And once I've done my plug-in with the units, I can just turn it into an equation. So what derivative can I take here? Well, what I can take here is the derivative of y with respect to time. What would that do? Well, that says, how does the y position change as a function of time? So dy dt is equal to here ddt of 20t plus ddt of negative 4.9 t squared. And so that's just 20 minus 9.8 t, dy dt. So that's how y changes as a function of time. But what can I do with that? Well, if I set my dy dt is equal to 0, boom, coming over here, I get t is equal to 20 over 9.8. And what's that? I don't have my calculator on me. I should have grabbed it. 2.1 seconds or so, give or take. Right? I should have grabbed my calculator before doing this. The numbers are not really that relevant. But the idea here is, notice this process didn't give me my maximum height. What this process gave me is, at what time is the function minimized or maximized? It told me where the turning point was. So when you're doing min-max problems, the derivative you're taking is not directly finding you your min or your max. It asks the question, at what variable this does the min or max of this function occur? So at what t does min or max y occur? Right? So that's part of, in some problems, we have to figure out what derivative we want to take. Here, the problem doesn't really tell me that what I'm taking here is a derivative with respect to time, but because the function is with respect to time, that allows me to do this. And then if I wanted to know that maximum height, then I would then evaluate the function at t equals whatever it is I found there. Boom. Now, how do I know what I found is a maximum? Now, this problem presupposes that you're going to find a max. But let's say the problem asks you to find out all turning points, right? Well, what would I do? Well, what I would do is I would take the second derivative of this now. So I take ddt of y, and that would give me ddt of 20 plus ddt of negative 9.8t, and that just gives me negative 9.8, right? And so d squared y dt squared, oh, notice d squared y dt squared is always negative when dy dt is equal to 0, and that's how I know it's a rel max, because it's concave down when I reach the turning point. It's got to be a rel max. And so if you need to prove whether the thing you found here was a min or a max, right, if the problem doesn't presume it, then what you're going to do is you're going to do a second derivative test in order to do it. Okay? So that's the general idea here. Set up a function, take the derivative of it with respect to some variable, set that derivative equal to 0, and solve. And so what we're going to do here is look at a couple of problems on the applications of derivatives. So here we go. We're going to do number 2 as a sample, which says the sum of two positive numbers is 20. What is their maximum product? All right, so what we need to do here is set up some sort of function. So let's decode our knowns. Well, we have two positive numbers. Let's just say let A and B equal two positive numbers. Because you have to, in this type of problem, create variables. If we're not doing a physics problem per se, where the variables are set out for us, we got to create them in this way. So we know that the sum of them, A plus B, is 20, okay? And we're looking for their maximum product. So if I say P, and we say let P equal product, is equal to A times B. What we're trying to find here is, what is this maximum product? Now notice here, I can't take the derivative of this equation yet because I've got two variables in it. And this is often true with the min-max problems. Oftentimes, what we have is the one equation we're trying to maximize that has the thing in it that we want to maximize, and then something else called the auxiliary equation. And the auxiliary equation is sometimes called the linking equation, because oftentimes the main equation has multiple variables in it, but in order to do this process, we need this main equation just to have the thing I'm maximizing and one other variable in it. Now, it sounds like I'm belaboring the point here, which I kind of am, but this is a very simple problem. I'm trying to highlight a methodology that gets used often in these min-max type problems. So what I'm going to do is I'm going to take my auxiliary equation, and I'm going to say B is equal to 20 minus A. And now I can put my main equation entirely in terms of one variable. So there I go. And actually, let's put that in a nice format here. And now I can very easily take a derivative. And the derivative I can take here is with respect to A. So what am I doing here? What I'm doing here is I'm asking the question, or trying to solve, what this does is, what value of A gives a max product, or P? So here we go, dP dA is equal to dDA of 20A plus dDA of a negative A squared. And so that gives us 20 minus 2A dP dA. And then what I'm going to do is I'm going to set that equal to 0, and then I get that A is equal to 10. So the value A equals 10 gives me the max product. And so now to find P max, I would plug in my max, the A that gives that max. So that's 20 times 10 minus 10 squared, which of course is 100. No units on this because the values they gave us didn't have units. Oh, that's sort of interesting. A is 10, notice B is 10. What we just proved is that of the rectangles, the square gives you the maximum area, which is something that you probably encountered before in math. but there you go. I know it's a max, by the way, because if I just look at this, the second derivative here is going to be negative, and so that's going to be that. Also, the problem presumes a maximum product and doesn't ask you to prove whether the product you find is a max or a min. It's got to explicitly ask for that proof before you do it. Let's do another problem there. Let's look at number 5. So 5 says, there are 50 apple trees in an orchard. Each tree produces 800 apples. For each additional tree planted in the orchard, the output per tree drops by 10 apples. How many trees should be added to the existing order in order to maximize the total output? Okay, so what I'm looking for here is total output max, right? So TO, that's really gross. Let's actually give it a variable. Total output max, or total output, we'll just call, I don't know, capital T, okay? So some let statements here. And so for each additional tree planted, let's say each additional tree is equal to n. So n is the number of additional trees, right? All right, so let's see what we have here. So that means the total number of trees I probably should have used that for T, for total number of trees, is equal to, I don't know, we'll call that Q, right? So therefore, I can create an equation for Q. Q is going to equal, well, initially there are 50 trees, right? And then for each tree planted, so that's just going to be Q is equal to 50 plus n, the total number of trees. Okay, and so now total output says the total output, T, is going to equal, let's see, initially each tree produces 800 apples. So that's 800 apples times the total number of trees, that's Q. But for each tree planted in the orchard, the output drops by 10 apples. So minus 10 times n. Right? Oh no, that's not right. So what we want to do actually, that's terrible, is we know that the output of a tree, there it is, the output of a tree, an individual tree, is 800 minus 10 times each number of trees. And so the total output, T, is the output per tree times the total number of trees, Q. Right? So I'm actually going to write that. So the output per tree times total number of trees. Okay, cool. So I've got that. So now what I want to do is I want to get this in terms of one variable. So I think the way forward is pretty straightforward here. That's 800 minus 10n. Q is 50 plus n. And since I want to then maximize T, I'm just going to do a little work here to start out. So that's 40,000 first outer plus 800n minus 500n and then minus 10n squared. Let's neaten that up. 40,000 plus 300n minus 10n squared. Okay. Great, so there we go, T. So what I want to do here is find out how many additional trees gives me the maximum output. So I want to take the derivative of T with respect to those number of additional trees. So dt dn is equal to ddn of 40,000 plus ddn of 300n plus ddn of negative 10n squared. Okay, so looking at that, what do I have? I've got dt dn equals 0 plus 300 minus 20n. And I know I'm going to set my first derivative equal to 0 to get my answer, and that means n is equal to 15. So I would want to put 15 additional trees. Let's see what the question is asking. How many trees should be added? Perfect. So I'm actually done. I should add 15 trees. The question does not ask what is the total maximum output, but that's an easy enough thing to do. I would just do T as a T of 15 and plug that in order to find out the total maximum output that I can have. Right? So here we have to set up the two equations from the word problem and then mix them together, take the derivative, and then do my interpretation work. Here, it applies the maximum output, so I don't need to do that second derivative test. So you'll do some practice with these min-max type problems.